Okay, so we just wait for like 1 or 2 more minutes for everybody to arrive, and then we are going to start, okay? So I think we should now be ready to start the lecture. So Alexis, if you could start the recording.
Yeah, it's already started.
Okay, so welcome everybody from my side. My name is Stefan Jakobek. Maybe some of you know me from the previous lectures. I'm going to hold the rest of all this lecture, which starts today and is probably going to end by mid or the end of May. And if we just start by looking at the table of contents. So what you've seen so far in the lecture was, of course, the root locus method, which was some introduction. And then we moved to system analysis in state space. So you learned how to model state space models by itself, so model physical systems in the state space, how to analyze systems in the state space. For example, controllability was something very important, how to analyze for stability, for example. And then you moved on to the controller design in state space. So we used the pole placement, the so-called Ackermann formula, which we are going to use today also. And then the last chapter, which was started right before Easter, was the first one where you move to nonlinear systems. So the describing function is one approximation method to treat and analyze and also control nonlinear systems. You treated the idea of limit cycles. So what happens if there's for example, a discontinuous controller and you apply it to a linear system. But all in all, the describing function method was an approximation. And from now on, we are going to treat nonlinear systems, and we are going to treat them in a more or less exact way. And the first chapter that we're going to start with is feedback linearization. And although linearization, as you know, it sounds like an approximation. So we take a nonlinear system and we linearize it around an operating point. This idea is somewhat misleading. What we do here is we apply a nonlinear transformation. That takes me right to this system here, to this chapter. We apply a nonlinear transformation to a nonlinear system in order to make it a linear one. So that's the basic idea about feedback linearization. And let me just go right through the chapter. And I tend to start with very simple examples to show you what everything is about. And I'm going to do this right here. So there's a very simple motivational example. Consider this this ball here. So it's some kind, it looks like a glass, but it's actually a nonlinear ball. And you see that depending on the fluid level, obviously there is some feed flow here. It's called U. This is our actuating variable. So assume there is some kind of pipe and you might open or close it. And then depending on the actual level, which is denoted by H, there is a certain cross-section surface level, which is called A of H. And obviously in this case, it's diverging. So the bigger, the bigger the level, the bigger also the surface is. And then of course there's some outflow. We assume that there's some kind of valve, an outflow. And given all this data, we can derive a very simple nonlinear differential equation, which is actually a a mass balance or a volume balance. So first of all, what we see here on the left-hand side is the actual amount of change in volume in the tank. So this is A of H times H dot. This is the amount of change that happens. And of course, this is just the net balance of everything that goes in, which is U of T, obviously, and what goes out. And this is this term here. And you probably know that this comes from the so-called Bernoulli equation. I just denote this here. Bernoulli equation. And obviously there is some coefficient A that denotes the friction here in this pipe, and then it's proportional to the square root of H. So obviously this is a nonlinear differential equation for two reasons. First of all, because of the Bernoulli term, and secondly, because we have a nonlinear cross section that follows some law depending on how this ball looks like. So this is a nonlinear differential equation. And let's assume that we want to control the level in this tank. So this is a typical control task that you might have to solve. And then feedback linearization, if I had to explain it very simple by means of this very simple example, it actually comes like a trick. And this is given here. If we choose the control law U of T in the following way, look at this. So U of T is equal to A times the square root of this expression here, plus A of H, so this is the cross-section formula, times some new variable, which we call nu. Nu is called an equivalent input. Let's assume that we just have this control law. Somebody told us to use this control law. What happens if you take this U of T and insert it into here? Then obviously what you can see is that this expression here is cancelled out by this one. And because A of H is multiplied by H dot and also here by the so-called equivalent input, we are left with a very simple expression, which is this one. So H dot is equal to nu. So what does this mean? Why do we proceed in the way we did it here? We call nu a so-called equivalent input. Why is this so? Because it appears here on the right-hand side and tells us what H dot is going to be. This is one thing. Secondly, we see that we got rid of those nasty nonlinear terms, namely the nonlinear cross-section and this so-called outflow term. So how did we achieve it? We did it in the following way. First of all, we added this term to the control law. This was one thing. And secondly, by choosing the equivalent input in such a way that it had to be pre-multiplied by A of H, surprisingly, or in a good way, it simply disappeared in the equation. And what we are left with is a linear differential equation, if you want to, which is a very simple one because it just tells us H dot, so which is the first derivative for H, is simply our new equivalent input. So this is, I think, a very good first step towards generating a nice control law. If we just know that by choosing this value in the proper way, we can design how H dot is going to behave. So the only thing that we still need here is a control law. And that in this introductory example, I just chose the control law in the following way. We denote, so first of all, there's some desired level. So HD is a desired tank level. This is the control error that you have here. And then we choose the equivalent input to be like proportional to this control error in some way. Okay. If we do it that way, then we get closed loop dynamics in the following way. So this is H dot plus alpha times H minus HD is equal to 0. So what you can see here is that this differential equation is already a linear one. And if we take the original control law, which is given here, and insert it into this equation, eventually we get a nonlinear control law. So what you see here, and I'm going to repeat it, it's probably a little bit complicated, but in the first place, we had a nonlinear differential equation. Then by some trick, we chose an input law, control input law, which looked like that. And eventually we got a nonlinear control law along with a nonlinear differential equation of the system, that resulted in the linear behavior of the system. And this is all what the feedback linearization is about. So let me repeat this in some different words, so to say. First of all, there's the nonlinear differential equation. Secondly, we chose an input in such a way that this nasty nonlinear term, the first nonlinear term here, is cancelled out. We simply cancel it out. Secondly, there was a way of using or transforming a new input, which we call nu, in such a way that the second nonlinearity also disappeared. So equivalently, or in the end, we are only left with this very simple differential equation. And if you look at this, control law, it actually contains. It's not yet a control law. It's simply a nonlinear transformation. It contains y, which is our only state, and it contains y again, of course, here, and the new input. And by doing this, by applying this nonlinear transformation, we get a linear system. And this is the reason why this method that we are discussing here is called feedback linearization. So we have some feedback from the state here and here. And by applying this control law, we get a linear system. So we actually apply a nonlinear transformation to the system in order to get a linear system behavior. And then, of course, depending on the particular control law that we chose, just see that my pencil has died. Hang on for a second. Okay, so I have to continue without it for the moment at least. By proceeding in that way, we get a linear state differential equation. Back here it works again. I'm happy about that. So this is the overall trick, or the only trick in feedback linearization. Then of course you might choose one or another control law in order to complete this. This is the idea. Now let's highlight this in a more general way. We assume that we have the following structure of a nonlinear system. First of all, this is the state equation. So x dot is equal to f of x plus g of x times u. This is a very special form, which is called the so-called input-affine system representation. So you can see that this right-hand side of the state differential equation is a nonlinear one, obviously, but it's actually linear in u. So you might argue that this is a very special representation. It's a very restrictive assumption that u appears linear. Actually, according to my experience, in more than 95% of all nonlinear control systems, the input appears in this more or less linear form. There are some mostly chemical plants where this is not the case, but in most examples or in most systems that you encounter in mechanical engineering, also electrical engineering, and even in chemical engineering, it simply has this form, and you can use this. Secondly, there's an output equation which looks like this. So y is h of x. So we assume that there might be some nonlinear function of the states which forms our output. Mostly it's actually a linear one because the states are pressures or masses or whatever, but it might even be nonlinear. So this is what we start with. And before I actually go into the mathematical details, I want to show you what we are up to. So I'm just skipping this and I'm returning to these equations in a minute. Let's just look at what we are up to. First of all, we are looking at a nonlinear state transformation, which is this one. And secondly, we are looking at a nonlinear control transformation. So you see, this is the new artificial or synthetic input, pretty much the same as you had in this introductory example. So there are some funny, strange expressions, and there's the actual control input. So we're looking for such a control law, and we are looking for a certain state transformation, which is given by this. So this is more or less always the same. So we use as the new states the output, the derivative of the output, the second derivative of the output, all the way to the n minus first derivative. This is the nonlinear state transformation that we're up to, and you're going to see in a minute that this makes the overall transformation, the overall view at the system pretty easy, and it actually leaves us with a linear system representation. Let's take a look how this works. So first of all, we start out with the output. So what you can see here is, and this is the reason why I showed you this in the first place, that the transformation actually depends on the chosen output, okay? So if for any system you choose a different output, then of course the transformation will be different as well, okay? So let's look at the output. What is the time derivative of the output? Y dot, and we can express it in terms of h of x. So this would be the time derivative of this expression. And obviously, we can apply the chain rule. So this is the derivative of h with respect to x1 times x1 dot, derivative of h with respect to x2 times x2 dot, all the way through xn, okay? And we express this in the following way. So this is dh over dx times x dot. And this expression obviously is a gradient. So h of x is some function that depends on all the elements of the state vector. And this derivative is the gradient. So what we get here is the gradient of h with respect to x times x dot, okay? And if we substitute the right-hand side, which is given here, then we get this expression. So you see, although it might look very complicated in the beginning, you can actually substitute and you get this expression and that expression, okay? And in order to make things more simple, we now introduce some new mathematical terminus, which is called the Lie derivative. And the Lie derivative is simply this one here. So if we take some function, some scalar function c, which depends on the vector x, and if we look at the gradient, which you can see here, this is the gradient of c with respect to x, and we multiply it by some vector field a of x, then this is called the Lie derivative of c along a. So this might sound very strange to you if you hear it for the first time. And I think there's a very hands-on expression for us as mechanical engineers. Let's assume that c of x, for example, is a pressure distribution. So x is a spatial coordinate. So it's the coordinate, for example, in our rooms. Everybody now sits at home. So you have a coordinate in your room, in your apartment. And c of x, imagine that this is a pressure distribution, or maybe it's more hands-on to imagine this, as a temperature distribution. So it's warmer, maybe in your window today, because the sun is shining, it's colder somewhere else in your apartment. So c of x is the temperature distribution in your apartment. So this gradient is actually the change, the vector that points in the direction of change in temperature at every point in the room. And then a of x might be it could represent, for example, some velocity. Imagine that there's a fly or a bee flying through your apartment, and a of x is the velocity vector of the bee. So it just follows a certain trajectory, flies back and forth. A of x is the velocity vector. And then if you take this product, this is actually the change of temperature that bee experiences as it flies along its trajectory. So it could be expressed or seen in that way, okay? Or for example, imagine a stream, for example, the Danube, and then a of x is the velocity vector. So if you look at the stream from above, for example, if you go on the Reichsbrücke or on the Nordbrücke, these are both bridges that span the river Danube. And if you look at the river from above, you will see the velocity vector. So every single particle follows its own designated trajectory. And again, if you imagine that this is, for example, some temperature or pressure in the flow, this is actually the change in pressure that every particle experiences, okay? So this is what we also call a convective derivative, okay? So for our purpose, we call this the Lie derivative, and it's, I think, a very nice abbreviation. So it simply designates that this is the change, the change of c of x along the vector field in A, okay? And if we use this, then this first derivative of y can be simply denoted in the following way. So it's LF h of x. So this is the change of h of x along the vector field f, which is the first one here, plus LG h of x, which denotes the change of h along the vector field given by g, okay, times u. So this is how we proceed. So this is our new terminus. So in most technical systems that we encounter in control theory, this derivative is equal to 0. So what does this mean? If we look at equation 5.1, we see that y dot, if this expression is 0 for all x, I have to say, then it means that y dot only depends on this one here. So it essentially only depends on the state vector, but it does not depend on the input vector u. Okay, so it would look like this. So this is also very important in terms of control theory. It tells us that in this system here, with our input signal u, we are not able to affect the first derivative of the output, okay? This is what it means. So if this is 0 for all x, it might be 0 for all x, it might be 0 only for some x or for most x, but if it's always 0 like here, then we are not able to affect the first derivative of the output, okay? So if we carry on with the deriving the output with respect to time, then, for example, we would get something like this. So this is LF squared times LF squared h of x. So what does this mean? It can simply be derived in a recursive fashion. For example, if we take this equation, for example, we can simply write it that way, y dot, that's equal to d over dt of LF h of x. And at this point, we could only imagine that LF h of x is a scalar function of the state vector. So we could write it that way, d over dx of LF h of x times x dot, okay? And that would be d over dx. So again, this is the gradient of this Lie derivative that we've just computed. So this here is a gradient, okay, times, and then we would have f of x plus g of x times u. And then apparently we could define, sorry, we could easily define this to be LF squared h of x. So LF squared h of x is simply obtained by consecutive evaluation of this derivative, if you want so. And obviously the other term, like d over dx times g of x. So that would be the inverse, that would be the derivative of this expression here along g, and we denote it by LG LF h of x. So obviously there's a certain logic behind this, and you've probably only heard it the first time today in this lecture, so you have to get used to it in some way. And as we go along with the lecture, you will see it several times. So in this way, we can carry on with computing the derivatives. And what we do here, you see that this derivative doesn't show up here. We assume that almost all of these derivatives with respect to the input vector g of x are 0. Okay, so we assume that those derivatives are 0 for the basic function, for the output, obviously, for the first derivative, derivative, for the second, for the third, and so on, all the way through theta minus 2. And then only in the derivative with the which is here indicated by theta, we see the input. Okay, so this is the normal situation. Whenever you model a system, and you will see this by a number of examples in a minute, we see that certain outputs are not influenced by the input u, and only once we arrive at a certain derivative, we see the input. So this has a certain consequence for controlling the system, namely that we are only able to affect the derivative of order theta with the input. All the lower derivatives cannot be affected. And this also means that we are only able to, for example, control certain trajectories of the output. So we are not able to, for example, have a trajectory where the first derivative changes discontinuously. So this has certain effects on the controllability. For now, so for today, for the lecture today, we assume that this derivative, where the input shows up for the first time, is exactly equal to n. So it's equal to the state, which is very important. In terms of names, this integer theta is called the relative degree of the system. Okay, it's called the relative degree because it tells us what is the difference between, so to say, the actual output and its derivative theta, where we actually are able to affect it by our input. This is the reason why we call it the relative degree. For today, we assume that this relative degree is always equal to the state order, which has a certain meaning, as you're going to see in a few seconds. Okay, so this brings me to what I've just shown you before, to the state transformation. What we do here now is we take as a new state variable C1 the output y, C2 is equal to y dot, C3 is equal to y2 dot, all the way to the n minus first derivative. And you can see if we take all these Lie derivatives that we have just computed recursively before, and we have to put them in here. So you can see, obviously, in order to get this transformation, it has to be nonlinear. So you've only heard about linear state transformation thus far. This is the first time where you can see that in order to get this new state vector, we have to apply a nonlinear function of x. Okay, and obviously, in order to work with this, there have to be a few assumptions that we have to make. First of all, t of x should be continuously differentiable, so it should not be discontinuous. And obviously, we also have to compute the inverse function. So if we know c, we want to know x. So there must be an inverse function, and also this inverse function has to be continuously differentiable. And if this is the case, this transformation is called a diffeomorphism. So if t is continuously differentiable, if there's an inverse which exists, and if it's also continuously differentiable, then this transformation is called a diffeomorphism. Okay. So how should we work with this, and why did we proceed in the way we did? So why did we actually chose the output and its derivative as the state transformation? This has been done for a very simple reason. What happens if we take the new state vector and if we take the time derivative? So C1 dot would be y dot. So this is very simple. C1 dot is simply C2. C2 dot, which would be y2 dot, is simply C3, okay, which is denoted here. So what you can see here by applying or by using this particular state transformation, the system dynamics is essentially linear. So the derivative of any particular state is simply the next state. C2 dot would be C3, C3 dot would be C4, all the way through Cn dot. If we arrive at Cn dot, you can see there's a certain problem. It doesn't look so neat anymore. Cn dot, by definition, if we take this equation here, Cn dot is equal to this nth Lie derivative of x plus this Lg, Lf to the n minus 1 times h of x times u. So it looks a little bit nasty, all these lower derivatives are pretty nice. It's linear dynamics. The only thing that we have to get rid of is this one. And we do so by simply taking Cn dot, which is nothing but y, the nth derivative of y, and this is this, and we assign a new synthetic input. And it's pretty much the same as we did with this introductory example. We just take the highest derivative of the output, which is this one, and we say this is our new synthetic input. And of course, this is equal to this equation here, okay? So just to sum this up, and I think this is the most complicated part of this chapter, and you have to understand that everything else is, I would say, pretty much easy. Let's just recap it. So we started with this state equation, and of course we had this output equation. And then we started to compute the derivatives of the output. And we did this in a consecutive fashion. And we observe, and we do this with every dynamical system, that normally in the first derivative, the input does not appear. Also, it does not show in the second derivative, and so on and so forth. It only shows up in a certain order of the derivative, which we call theta, and theta is the so-called relative degree of the system. Okay, for this part of the lecture, we assume that the relative degree is equal to n. You will see that everything is pretty easy in this case, and then we can actually apply a nonlinear transformation, which is this one here, which is C1 is equal to y, C2 is equal to y dot, and so on and so forth. We do so because we observe that if we take C dot, the time derivative of C, we see that each one state derivative is simply the next state. So C1 dot is C2, C dot is equal to C3, and so on and so forth. The only problem that we get is with the derivative of the last state, which is that one. And we just circumvent this by taking this nonlinear expression that we have here, and we assign it a new synthetic input, which we call v. Okay, if we do so, the new system that we arrive here is simply this one. It's simply a chain of integrators. So this here is C1, and we know that C1 dot is equal to C2, which is here. So C1 dot is equal to C2. C2 dot will be C3, and so on and so forth, all the way until we arrive here, and that would be Cn dot, which is equal to the nth derivative of y. So essentially what we did here, and this is the reason why this is called feedback linearization, we actually applied two tricks. First of all, we had this nonlinear state transformation, and secondly, we had this nonlinear input transformation. So this is the actual physical input, and this is our new synthetic input, which is always equal to the nth derivative of y. And of course, in order to apply this transformation, we have to know x. So that's the overall trick, which is in feedback linearization. And if we apply both transformations, both the state transformation and the input transformation, we always get something like this, which is a chain of n integrators. So this is altogether, these are n integrators. So when you sum everything up, the new transformed system looks like this. So as I've explained before, C1 dot is equal to C2, this is C2, C2 dot is equal to C3, and so on and so forth. And in the last equation, we just write Cn dot. Cn dot would normally be this nasty nonlinear expression, but since we have applied a new synthetic input like this, it's simply like this. So Cn dot is, it does not depend on any of the states. It's simply equal to 1 times v. So that's a trick, okay? So the nice thing about this is, once you have arrived here, you can already apply all the theory that you have learned about state feedback control in the preceding chapters. So you can apply the Ackermann formula, for example. You can apply pole assignment as you've learned it. The only thing you have to observe is you apply all your control design in this linearized world. So it depends on the new state vector C, and then on the new, the control law will give you some result for the synthetic input. And then you have to go back, so you have to observe that your actual input is this one here, okay? This guy here. So this is actually the only trick about feedback linearization. So once you have understood everything up to here, you will also understand the rest, and this is the only real demanding mathematics if you want so, okay? So if you take this equation here, and if you solve for u, because this is our actual physical control input, then you will get this. This is the actual nonlinear control law, okay? So what you have to observe is in this world, in this linearized world, you can actually assign any control that you want. It could be the Ackermann formula, for example. It could even be PI control. Here in the lecture, I will just give you one example, which is the pole assignment that you already know. Let's assume, for example, that our synthetic input is simply some linear state feedback. So it's minus K transpose times C plus some pre-filter KW times W, and this is our desired value. So this is where we want the system to go. Desired output, okay? So this is exactly the control law that you already know. And if you apply it in that way, then you would get this form here, obviously. And because we are already here in the controllability canonical form, if you take this control law and insert it here into equation 510, you will get this here. And if you look into your scriptum, into your lecture notes in the preceding chapters, you will see that this is exactly the linear controllability canonical form, and the coefficients alpha 0, alpha 1, alpha 2 exactly match the desired eigenvalue configuration. So it's exactly the characteristic polynomial of the system. So I'm not going to write this out here on the whiteboard, but I will give you this as a mini homework. So this is also my style of lecture, to give you some little exercises that would actually help you to dwell into the system. So for this point, I would ask you to just prove that by having this controllability canonical form, the coefficients alpha 0, alpha 1, and so on exactly form the characteristic polynomial of the output. So this is very easy if you do it in that way, okay? So let's assume that you have just chosen some characteristic polynomial coefficients, and you can do this by the Ackermann formula, obviously. And then you get this control law, of course, and you take the control law and insert it into here. So this is where it goes, okay? And if you do this, you will get a very funny control law, because first of all, it's nonlinear, okay? So obviously there are some nonlinear functions of the state. Secondly, what you can see here, it depends on both x and c. So this sounds a little bit strange. So how do you get c and how do you get x? There are actually two possible ways to implement this control law. First of all, you can express it in terms of c, or you can express it in terms of x. And this is the more usual way to do it, because if you know x, then by this transformation, you know c, and then you will be able to express the control law here, insert into here, and then you're able to express the control law. There's one more thing I would like to point out, and this is actually a fractional expression, so it has a denominator, okay? And you can see this denominator, we normally assume it's different from 0. So if you remember here, we had a definition of the relative degree. I just scroll up here a little bit, okay? So we were assuming that all those Lie derivatives were 0, except for the one with the order theta minus 1. So theta minus 1, for theta minus 1, this is different from 0, which does not mean that it's always, hang on for a second, that it's always the same size. So there are many nonlinear systems where this expression is different from 0, but there are certain situations where it could become very, very small. And if it becomes very small, it means that our control input might become very, very big. And in the situation where it's actually approaching 0, we actually have a loss of controllability, okay? And this is very important also to note for you. In a linear system, if you remember, we had the controllability canonical form. And if the system was state controllable, then you were always able to transform to the controllability canonical form and everything was fine. In a nonlinear system, this expression here might become 0 for some points in the states, which means you're not able to control the system in that situation. This is very important to note, okay? Let's sum this up. If you look at this control law, there are actually two expressions. First of all, this one, and I just mentioned that C is equal to d of x, okay? Which means we actually have one part which only depends on the state, and I just use this abbreviation here, which is called R. And then there's another part which depends on the reference value. So this tells us where we want to go. And this is then actually the second part, which I denoted by Q. So everything is summarized here. So we have our R of x. It still depends on C. Then we replace C by this transformation. This is our Q of x, okay? And all in all, if we summarize this, we get this kind of block diagram representation. So this is the output. This is our state equation, so our state differential equation. We have one part of the control law, which is this nonlinear feedback. We have another part, which is, if you want, a nonlinear feed-forward control. Both depend on the states. And all together, if we look at the overall transfer function from W to Y, the system behaves like a linear system. Okay, so this is very important to understand. Everything here is nonlinear. The system itself is nonlinear. The output, of course, as well. The first part of the control law is nonlinear. The second one, and all in all, although everything is nonlinear, the system behaves like this. Okay, so I just put a red box around this to make this very obvious for you. This is our closed loop transfer function, and it's a linear transfer function. Okay. There's one other thing I would like to point out. Okay. Just by the way, if there are any questions, then just unmute your microphone and ask them, because right now I'm not able to see the chat window. I'm trying to fix this for next week, but today I'm not able to do this. There's one other thing I would like to point out. If we look at this control law, so there's the first part, which is this state feedback, and there's the second part, which is somehow dependent on the reference value. And now at this point, I would like to go back to our very first simple introductory example, which was this ball where we wanted to control the level. Okay. If we looked at the control law, which is here, again we have one part which only depends on the state, and there was another part that also depended on the reference. And if you look at it very closely, you can see that this part, which depends on the state, is actually used to compensate the outflow. Okay, so our input, which is the flow, that's the feed flow that goes into the system, is the first part that compensates the outflow, and the second part that is used to drive the system somewhere else. So this is proportional to the first derivative, and this is normally always the case. We will see it in a number of examples, that the input is always something which is used to sustain the current situation, the current state situation, and the second part, which is used to drive the system somewhere else, and we're using this for our control. So this is always a typical property of the feedback linearization, okay? And it's also represented in this, obviously in this form where we have the nonlinear feedback. If we take everything together, okay, so we have our nonlinear control law, which depends on C, and obviously C depends on X, okay, so this is C1, this is C2, all the way. So this is Cn. If we summarize everything, then we get something which is called the nonlinear Ackermann formula. So you see, you will have LFN h of x, which is taken here. And then you have all those coefficients, alpha 0, alpha 1, which are taken from the Ackermann formula, obviously. Alpha 0 multiplied by W, and everything is divided by this other D expression. So this is what we call the nonlinear Ackermann formula. So if you want to implement this, for example, in MATLAB or in Simulink, and we have a number of examples which we are going to distribute, you can use this so-called Ackermann formula. So you see, it's a nonlinear control law. The coefficients alpha 0 through alpha n-1 obviously are determined from the linear Ackermann formula only by determining the characteristic polynomial. And by applying this control law to the nonlinear system, we get a linear behavior. So this is the overall trick of feedback linearization. So I was very accurate on this, and I really spent a lot of time, because this is the essential part that you have to understand. Everything else are examples which just highlights the idea, but this is the actual idea of feedback linearization. So it takes some nonlinear transformations in order to make the nonlinear system behave like a linear one, if you want so. Okay. So let's stop here. And let's look at the first example. So this is, if I want, so a pretty artificial example. So it's a third order system, obviously. And it looks like this. So x dot is equal to some f of x, which is this one here, plus some g of x times u. And you see then g of x looks pretty nasty. It contains the exponential function. So e to the x2. And then times u. So this is our system representation, and our output y is simply x3. So sometimes h of x is really a nonlinear function, but most cases also in practice, it's simply some element of the state, or of the state vector. What you can see here is a number of Lie derivatives, and I'm going to show you this in a minute. What I would like to show you probably as a homework is, especially for these very simple examples, you can actually carry out these state transformations in two ways. This is, so to say, do it by the book, compute all the Lie derivatives. I'm going to show this to you in a minute. But you could also do it, if you want, so the old-fashioned way. And this is shown here. So I've prepared this before the lecture started. If you simply take that y is equal to x3, then y dot will be x3 dot, which is x3 dot is x1 minus x2. Okay, so this is y dot, and obviously it doesn't contain any u. Okay, so let's carry on with the differentiation. So if we have y2 dot, so that's the second derivative of y, that's x1 dot minus x2 dot. So simply take this result and carry on with the differentiation. x1 dot, let's take a look here, that x1 dot would be e to the x2 times u minus x2 dot. So x2 dot would be this plus this. So you see, fortunately, these two expressions that carry the u cancel out, and we're simply left with minus x1 minus x2 dot, x2 squared. And obviously, the second derivative doesn't carry or contain u as well. So I could carry on with the differentiation. So y3 dots, that would be minus x1 dots minus 2 times x2 dots. And then you could actually carry on and then enter these expressions. So x1 dot would be found here. x2 dot again is found here. So you might feel free to complete this as a mini homework. And to check your result, you should actually end up exactly with this expression. So this is one, if you want, so the old-fashioned way to do this. Okay. Now I show you the other way, which is the more formal one, which is the Lie derivative. And of course, obviously, with such a simple example, there's not much difference in doing it in the old-fashioned way or this one, but it shows you how convenient this one is. And of course, this can be also programmed. So in MATLAB or any any software tool where you have symbolic math operations, you can program this very easy. So let's take a look. First of all, this is the output. So this is x3, which is simply, if you want, so it's 0, 0, 1 times x, okay? So what is the Lie derivative of this along g or f? Let's check this out. So first of all, this is our scalar function here. And if I take the derivative along x, the gradient, of course, is simply 0, 0, 1. So this is the gradient of this function. Because it's linear, it's simply 0, 0, 1. And then I could either multiply it by g of x, which is this one, or by f of x. And then fortunately, this guy here is 0. And secondly, here you can see I only have to take the third component, which is this one. Okay, so these are our two first order Lie derivatives, if you want. So this one is 0, this one is this one. And now I carry on with the to compute Lie derivatives. So you can see here what happens if I take this one, and let me again express this as this is 1 minus 1, 0 times x. So if I take the gradient as, and if you remember, I just told you a minute before that the Lie derivative is the gradient. The Lie derivative of this one here along g or f is the gradient of this one. So the gradient is obviously 1 minus 1, 0, either times f or times g. So in this case, we get this guy here. In the other case, it's simply 0, okay? And now it's the first time it becomes a little bit complicated here for this Lie derivative. We have to compute this gradient. So this gradient obviously will be minus 1. Then the derivative with respect to x2 is not constant anymore. So it's minus 2 times x2. The derivative with respect to x3 obviously is 0. And then we have to multiply this by either f of x, which is here, or g. So you can see this is the way we compute Lie derivatives. It's the first time probably you have seen it in your life. You can see either do it the old-fashioned way, and I would really recommend that you try this as a homework, just to get a hands-on comparison. What happens if you do it this way? What happens if you do it that way? It's a good way to just get, I would say, used to these expressions and to these operations, okay? Now we have everything that we need to have in order to compute our control law and our transformation. Obviously here the state transformation is found here. So C1, C2, and C3 is equal to y dot and y2 dot. So it's h of x, which is x3. It's LF h of x, which is this guy here, and LF squared h of x, which is this guy here. If you just compare it to what I did here is, so that would be y, that would be y dot, and that would be y2 dot. And obviously, again, here we get the same result. So it's a good check that we did it correctly. And as I said before, a recommendation, if you complete this for your homework here, then you should get exactly this result here, okay? Or another way, or the other way around, if I would just write v, our virtual input, which is then the third derivative of y, and that would be LF third power h of x plus LG LF2 h of x times u. So this, let's just use these arrows here. You should get it out of here if you complete this as I indicated here. And this would be a good homework to check this, okay? So this is it's not our control law yet. It's just two transformations, namely the state transformation and the input transformation, which gives us this linear system, okay? So if you take this, this nasty nonlinear system here, and if it's subjected to a state transformation, which is given like this, and an input transformation, which is like this, we end up with this here. So it's a chain of 3 integrators. Let me just complete this. So there's V, it goes into 1 integrator, then it goes into a 2nd integrator, and then in the 3rd integrator, and that will give us the output, okay? So that would be C1, that would be C2. So obviously C2, C1 dot is obviously C2. That would be C3, and obviously C2 dot is equal to C3, and then C3 dot, that's equal to V. So that's how the story goes. And the nice thing about this, once you understood it up to that point, it's regardless of whether the system has an order of 3 or 20 or 30, it's always the same scheme that you follow here. If the system has an order of 15, then this matrix here will be a little bit bigger, but it has the same structure and the same procedure, if you want, so in the control design. Also, for example, if you have a 3rd order system and you design a controller, then in the V and C world, this controller will always be the same one. So once you apply the Ackermann formula, you can take it for good and apply it to every 3rd order system. The only thing that is different is this transformation law here, and obviously this transformation law. So this is the nice thing. In the transformed world, 3rd order systems always look that way. 2nd order systems always look in the same way as well, okay? So let's take a look at how to do the controller design. And this should actually not be new to you. The control design works in that way. So in this case, we have 3 poles to choose from, okay? And then you can, for example, make a comparison of coefficients, or you can apply the Ackermann formula. You're free to do that in any way. And then you apply the so-called Ackermann formula. So I'm not going into details right now. That would be a homework for you to apply this. But you can see here, this is essentially a nonlinear control law. So you can see the input U, obviously it's some state feedback. It uses the states x1, x2, again here also x3. It's nonlinear in its states, and it behaves in such a way that the nonlinear system will have a closed loop transfer function, which is like this, okay? So always remember, when you apply all those nasty nonlinear formulas, the closed loop behavior will always be like a linear system. You have a nonlinear control law for a nonlinear system. The overall behavior will be like this, okay? This is the nice thing about feedback linearization, okay? Let's look at another system. So this is not a fantasy system, a mathematical system anymore, but something hands-on. So we have some kind of a tank where there's a propeller, and we assume that this propeller is used to mix this tank. So maybe this is some pharmaceutical stuff, or it's a cement mixer or anything. And obviously we have to use a motor, an electric motor. So you see that's the electric motor torque that is applied. So we have an electric circuit. So there's some inductance, obviously. And then there is some resisting torque, M of T. And you know, whenever there's a propeller, those resisting torque laws are normally essentially nonlinear, I'm sorry. So you see, the electrical circuit is more or less linear. Obviously also the momentum balance. The only thing that is nonlinear in the system, this is the load torque. The load torque follows this characteristic. So it's proportional to the 3rd power of omega. And obviously in this example, we want to control omega. So this is what we want to control. And of course, for the DC motor, we have those relations that you probably already know, okay? So already from the system configuration, we could guess the system order. So we have a 1st order differential equation for this one, because there's an inductance here. And then there's the angular momentum balance here, which yields another 1st order equation, which is given here, okay? So you see that this system looks like this. It's mostly linear with one exception, which is here. This is this nonlinear resisting characteristic, okay? And once again, I recommend that at home, you just take this output Y and do this as a homework for yourself. So Y is equal to X2, which is, I forgot to mention this, of course, our first state is the electrical current. The second state is the shaft speed, which is omega. So if Y is X2, then Y dot would be X2 dot, obviously, which is found here. So this is X2 dot. So it's equal to Km over J times X1 minus K over J times X2 to the third power. And then at home, you might want to compute X2 dot. And so that would be your homework to do this by foot if you want. So let's look at a more formal way. And again, this would be the Lie derivatives. So for us, the output Y, so this is 0 and 1 times X. So dy over dx, to just write this out more formally, would be 0, 1. So this is our gradient. It's constant in this example, and it's found here. And then for the Lie derivatives here, we have to multiply the gradient either by g or by f. And luckily, in our case, g of x is also constant, which is a nice feature of it, okay? There is our f of x. It's a little bit more complicated. And this gives us the Lie derivative LF h of x. And you can already find it by comparison. If you compare this expression, it's exactly equal to this one, which shows us that obviously y dot is equal to LF h of x. And here, of course, LG h of x is 0. So there's no u here showing up. So let's carry on with this. So this is the expression that we're dealing with. And to carry on, we have to compute the gradient of LF h of x. So we're looking at this one, the gradient with respect to x1. So the derivative with respect to x1, that's Km over J. For x2, it's obviously minus 3 times K. Maybe I should use some spacing here to indicate that this is a vector element. So that's minus 3 times K over J times X2 to the second power. And obviously it's 0 for X3. And you find this, I'm sorry, it should not be 0. It's simply like this. And there's the gradient, as you can see here. And then you have to multiply this gradient again by f, which is not carried out here. It's not spelled out here. Eventually it looks like this. And then there's the LG times this expression, so we multiply it by G. And obviously it's different from 0 here, indicating that we have a relative degree of 2. And again we end up we end up with the nonlinear state transformation, which is given like this here. That's the nonlinear state transformation. And we end up with the nonlinear control law, okay? And it's not a control law yet. It just tells us, if you want so, I tend to say it's a control law. It just tells us how the virtual input, is related to the physical output. So in this case, although the system is pretty simple, you can see that this relation, this input transformation already looks simply pretty complicated, if you want. So it's again a state feedback. So it contains x1 and x2. Then there is some nonlinear expression. So what you see here, although it looks very complicated, it's always the case that the actual physical output, system input, is related to the virtual input, through some state feedback. And this is also, again, the reason why we call it feedback linearization, because in order to compute the physical system input, we need some state feedback, some nonlinear feedback information, which is given here like this, okay? And then, because this is a second order system, it's only a second order system, in the transformed world, it looks like this. So it's very simple. It's a chain of two integrators. So pretty much like in the previous example. In the previous example, we had a chain of 3 integrators and this relation between the states here. And in this case, it's even simpler. We only have 2 integrators. For the control design, I don't have to lose too many words. The only thing is we have to assign 2 poles, which is given here. And then you can apply the Ackermann formulas. In this case, we compute the state feedback vector. We can compute the feedback law like this. So there's alpha 0, alpha 1. It's from the Ackermann formula or from comparison of coefficients. And you see that the control law looks pretty simple here in our transformed world. So we have state feedback from the transformed vector z. There's our reference input v, and this is our virtual input. Now, if you take this virtual input, now I use just going across these 2 slides and put it in here, you can already guess from this expression here. Maybe you can also put it into here, because this is already complicated. This looks pretty simple. All in all, we get a pretty complicated control law. It looks a little bit clumsy, but all in all, you can see it's again nonlinear state it's linear state feedback, it's nonlinear state feedback, okay? And all in all, this is our nonlinear control law, okay? So also, if you implement this on a computer, you could do it in the following way. Let me just summarize this. If you implement it on a computer, you could start with this transformation. So first of all, you have your state. So it's x1 and x2. Remember, x1, this was our electrical current. x2 is omega. So we assume that this is measured. And if it's measured, then we can actually take first of all, the state transformation. Maybe let me highlight this. So this is the computer version to implement this. In the first step, we would apply the state transformation, so we know C. In a second step, we would compute the virtual input V. And in the third step, we would actually apply the nonlinear control law. So we have a number of Simulink examples, and Alexis Benadier would be happy to send them to you. And then you can actually look up in the Simulink examples yourself how we implemented these control laws, okay? So this is the reason how we did it. This is the way we did it. And again, you can see in the overall block diagram how the situation looks like. We have an almost linear system with the exception of this characteristic here. And then although this is an almost linear system, okay, you can see that the control law looks pretty complicated. So normally I would say in nonlinear systems and with feedback linearization, the devil is always in the detail. And this is a very good example. It's an almost linear system. We only have this very small nonlinear guy, if you want so. And nevertheless, we get a pretty complicated control law in order to control the system, okay? Good. Of course, thus far we had 2 examples, and in each of these examples, we ended up with a chain of integrators. It's a chain of 2 integrators here for this example. You can use also integral control. We know that in many cases, it's good to have integral control. Probably Professor Kotzek has explained it to you. In integral control, we apply a little state transformation, and instead of only using this feedback here, as you can see it here, we also append something which is this here, and this is the integral of the control error, okay? So you see, in the previous examples, we had n different coefficients, and by doing so, we increase the state order by 1. And why do we do this? The nice feature of integral control is, as long as there's a control error, so this is y minus w, if there's a control error, the new state variable p is going to increase. Let's assume that for some reason y is not going to reach w, so y is always a little bit too small. Then as an effect, the state variable p is always growing, so it grows all the time. And this means that the synthetic input in this case is going to be adapted, okay? How is this done? It's done pretty much in the same way as you've already learned it a couple of weeks ago, with one exception. The linear system that you control is always the same. It's this chain of integrators. So this is actually, together with this, is a chain of n integrators. So it's always the same structure, okay? And then you've learned how to compute integral state feedback control in such a way, okay? So you augment the system, okay? And then you have to check whether this augmented system still has full state controllability. This is the way how you do it. I'm not going into details right now, but you can find this in your lecture notes. Let me just show it in the in terms of a very nice example, which is concentration control. So it's another example. If you want to, from chemical engineering, we assume there's a tank with a propeller. There's a certain concentration in here, and then we have a feed flow coming from here, from the right. So there's a certain concentration of the product going in, and we are able to actuate a valve here, and which means that the feed flow, which is called V dot, is governed by this equation. So it's a first order system. So we assume that there's a PD1 element, a PD1 behavior between our input U and the actual feed flow. So this is normal for many systems, that if you open a valve here, the system doesn't react instantly, but there is some delay. If you assume, for example, that there is an electric motor driving the valve, it will take some time for this to open. So there's a PD1 behavior between this. So this is a reasonable assumption, okay? So there's a certain time constant. This equation, though, is still a linear one, so it's nice, and we don't have to get worried about nonlinear control so far. Now let's look at what happens in this tank. In this case, we're looking at a non-stationary molar balance for the concentration, okay? And there is a number of things we have to observe. So this is actually the change of molar mass of the product A in the tank. So it's the change in concentration in the tank times the volume. And then we have to consider that the volume in the tank might also change. So there is V dot. Obviously, there's V dot times CAE. So this is the amount of mass that goes in through the feed flow. And then there's this term that always shows up here. This is due to dilution. So if there's some feed flow going in, there will be some dilution. And then there is some funny constant here. And this is because there's some chemical reaction going in. So there's a reaction constant, which is called K, if you want so. And we assume that there's some chemical reaction going on here. So some of the product is consumed, and we assume that it depends on the square. So this is a normal assumption. So it's a nonlinear chemical reaction going on here. And if we want this reaction to go on all the time, then of course we have to control the concentration of Ca. So if some of it is consumed, we have to replenish it here. And again, you can see everything that we do here is essentially linear, with one exception, which is this guy here, okay? And again, so everything that I've just explained is, of course, found in your textbook, okay? And since this is a second order system, we have two exercises. First of all, design a normal state feedback controller without integration of the control error. And for a second time, do it with integration of the control error, okay? Now, I'm not going into all the details anymore. I'm just going to highlight where we have the nonlinearities, which are actually given here and here. So I forgot to mention this one. So we see here, there's a nonlinearity in terms of the actual flow here, feed flow, which is actually a state variable, and our concentration. So I'm sorry, I forgot about this. So again, the overall situation looks pretty simple. It's essentially a linear system. So there's a linear input vector here. This does not depend on the state. This equation here is linear. This term is linear, but we have two nonlinear terms. So let's take a look where this is taking us. First of all, there are some numerical values for us to make it easier to handle all the expressions. So it looks pretty nice right now. And again, my recommendation is also for this example, compute everything by hand. So the old-fashioned way. So this is Y, our output, which is of course the concentration in the tank. So Y dot would be X2 dot, which is this one here. So maybe just try it by hand, and let me explain for you how we do it with the lead derivatives. Again, because our output is simply X2, the gradient of Y with respect to X is simply 0, 1. And if we multiply it by G, it's 0. So this is nice, then we get full relative degree. If we multiply the gradient by F, our vector field F, obviously this is different from 0. It's something like this, and this is what you should get also here. Obviously, this is exactly this expression here as it should be, okay? Then, and I'm not going to fill this out by hand, we have to take the gradient of this here with respect to X. So you can see there's a constant expression here. Then there's something which depends on both X1 and X2, and one expression which depends on the square. And I'm leaving it to you to just check whether all those lead derivatives have been computed correctly. Maybe please do this at home. And I think it's very important to just get a hand on this and get used to handling all those expressions. What has to be pointed out is, of course, that the lead derivative of LFH of X along G is not 0 anymore. And what you can see here, obviously, is this lead derivative, and I mentioned before that this shows up in the denominator of our control law. Maybe let's take a look at this. It shows up in the denominator of the control law here. So it's very important to look at this and check whether there are situations where that could become 0. And obviously, what you can see here, this lead derivative becomes 0. Hello?
Yeah, you know.
Yes, please. Is there any question? No question. Okay. So what you can see is this lead derivative becomes 0 if X2, which is the concentration of the tank, is exactly equal to the concentration in the feed flow. So what does this mean? It's not a coincidence that we get this mathematical expression. Just imagine that we want to control the concentration of Ca in this tank. If the concentration of our feed flow has exactly the same Ca as we see in the tank, then there's no way to change it, at least for the moment. So this is very obvious, okay? If you just assume that this is the concentration of salt, so let's assume that this is salty water, and if you apply fresh water, then of course you're able to dilute. But if this is also salt water, and if it has the same concentration as we see in the tank, then obviously there's no way to change it. So this is very obvious, and it's simply a sign that we have done all the computations correctly. So if X2 approaches the concentration of our feed flow, then we get a problem in controlling the concentration, okay? So it's very important. So let me just add an exclamation mark to examine this. Okay, we're also going to see it in a second example then later on. So again, what we can see here is we get our state transformation. So C is T of X, which is this transformation. We get our input transformation, which is again pretty complicated. And again, let me point out that it relates our virtual input to our physical input. And again, we simply get a chain of two integrators. We carry out the, or we apply the Ackermann formula, which is an easy thing to do. And we get our nonlinear Ackermann formula. And you can see it's pretty complicated if you want. So it's pretty complicated, but if you have to apply it on the computer, it's actually pretty easy, okay? And again, observe that if X2 approaches the concentration of our feed flow, which is here 0.72, then we get a problem, obviously, okay. Good, and then this is the result figure. I'm going to refer to that later. If we want to apply integral control, then of course we have to augment the system, but this is pretty much the same as you already did it a couple of weeks ago. So we have to augment the system, and maybe this is a good point for you to look this up in your lecture notes. And it's very important to note whenever you do integral control, the order of the system is increased by 1. So it's like this, okay? So it's a third order system now. We have to choose a third pole, okay? And this is, let me point this out by means of this equation. It's very important to understand in integral control. This would be your characteristic polynomial if there was no integral control, okay? There's no way it's not correct to just apply your ordinary Ackermann formula and then just to add some integral control. This cannot be, you can do it, and then many times you might be lucky and it works. But you have to understand, by adding minus alpha 0 times the integral of y, you actually add some other feedback here, and it has to be understood that you get another closed loop transfer function. This is very important in integral control for state feedback, that there's another feedback control, and that you have to take everything together. So you have to apply the whole state feedback at once. And you can, there's no way to determine alpha 0 separately from all the other coefficients. This is very important to keep this in the back of your mind whenever you apply the control. So here we get a characteristic polynomial. So you see this is the same closed loop poles as we had before in the second order system, plus a third pole. And then, and then when you apply Ackermann's formula, obviously, you see that you get very different coefficients. So those two coefficients used to be, here they are 5.5 and 6. And in the previous example, they used to be very different, okay? So this is very important. So oftentimes people try to neglect this, so they have just designed the state feedback control, and then they add some integral control without observing these rules. And then it works nicely, and at some stage it crashes completely, or the plant goes unstable, and this simply must not happen. So you see what we did here is we checked for the controllability matrix of the augmented system, which we had to do. And obviously this is in an invertible matrix, so it works. And then this is also the reason why we can apply Ackermann's formula, okay? And then of course you can see the closed loop step responses of both systems. And obviously they look very similar. And of course there is a little delay for the system B, which has the integral of the control error. So this is always the price that you pay. If you have integral action, then of course you will get rid of any control error, but the system is normally a little bit slower. This is normally so the price that you have to pay. Okay. So I'm going to conclude today's lecture with, if you want to, with a fun example. But I think it's also a very nice one. I created this example many years ago actually for a motorcycle company, which is KTM, which probably many of you know. This was actually for a motorcycle simulation, and they wanted their virtual driver to be able to do this, which is the motorcycle wheelie, For one reason, of course, because motorcycle riders probably are playful, but for another reason, because they wanted to test in their simulation the stress if they do this motorcycle wheelie, the stress on all the structures, and obviously also on the drivetrain, on the chain, and on the spokes. So they simply wanted to create this simulation test, and for this reason, they asked me to create such a control that would actually closely replicate what drivers normally do. So what you can see here, this is a simplified version, of course, of everything. So you can see this is the motorcycle plus its rider. So the S denotes the center of mass. And obviously, this is the pull of gravity. So this is M times G. And we assume that this height is denoted by H. And then there is some distance here between S and the rear axle, which is L0. So there's the wheel radius. And then there are actually two state variables. The first one is X, so this is the longitudinal motion of the motorcycle, and then there's phi, which is actually the pitch angle. And then, because this is a simplified version, we assume that we are able to directly control the force, the longitudinal force on the wheel, which is of course simplified, but it's good enough to explain you everything. And then there are two equations of motion. First of all, this is the longitudinal motion, which is given by this equation. So x2 dot is equal to F over m. So obviously there's the mass that comes into play plus phi 2 dot. So you can see that if there is some pitch motion, of course, it's coupled to the longitudinal motion, as we obviously all know. And secondly, there is the angular momentum balance, which you can see in the second equation. And you can see obviously that the force here comes into play. And if you want to, you can check these equations, or you derive them by yourself, of course. What you have to observe here is obviously that these two state derivatives are somehow coupled. So you have to decouple them, obviously, which we did for you. And you have to observe that, of course, it's only this is only valid if phi, if this pitch angle is greater than a certain minimum angle, which is when this wheel comes down, obviously. Okay. So everything collected in the form that we need to do the feedback linearization is like this here. Okay, so you can see that x dot is equal to this here. So x2 so x1 dot is equal to x2 dot is equal to this one here. So I forgot to mention that. So x1 is obviously phi, the pitch angle. x2 is phi dot, the pitch angle speeds, obviously, and then this is our input, which is the force. Okay, so in this model, I simply eliminated x and used it. I'm going to use it later on in the simulation. And of course, as the output, we use x1, which is phi, which is the pitch angle. So in this case, everything looks a little bit more complicated, and I'm only going to take a brief look at the lead derivatives. Obviously, LGH of x is 0, which means we have full relative degree. So we have a second order system. The input does not show up in the first derivative of the output, which is good. And secondly, LFH of x is simply x2, which is natural, of course, because we just assigned that x1 is phi, x2 is phi dot, so x1 dot obviously should be equal to x2, which is just a sanity check if you want. So secondly, what we see here is LF squared. So we have to take the gradient of this guy here. So we have to take the gradient, which is 0, 1, multiplied by f, which is this one here, which gives us this expression here. And then there is this LGLFX, which is equal to this expression. So as I mentioned before, whenever we compute this, let me highlight it, we have to check, because it shows up in the denominator of our control law, we have to check whether it could become 0. And you can see here, because there's some term here, which is ML0 squared plus J, which is always positive. So this is greater than 0. And then depending on the overall configuration, you can see here. So this is the sine squared of x1. So this is obviously greater or equal to 0. That it might be the case that this could become at least very small. So you can see the sine of x1 is at most 1. So it's sine squared of x1 is always less than 1. And so this overall expression is always different from 0, but depending on the inertia of the motorcycle, it could become very small. So it depends somehow, if you want, on the ratio between L0 or m times L0 squared, which is an inertial radius, if you want. So in relation to the inertia, then it might become pretty small, if you want so. Okay. Everything else just goes by the book. So we have our transformation C is equal to d of x, which is equal to these two Lie derivatives. Then we have our control law, which is like this here. Okay, so I'm just skipping all the math, of course. Now, there's one thing which I want to point out. Again, this control law relates our virtual input V to our physical input U, which is the force. Just remember, the physical input U is the force that has to be applied at the wheel base, okay? And remember, I just mentioned this a couple of minutes ago, that this transformation law always comprises two things. First of all, this expression here, which is somehow used to sustain the state. And the second expression here, which is somehow used to drive the system. And if you look at our system, our physical system, you have to understand that this is actually a physical system, and the force here that is applied at the wheel base is used for two purposes. First of all, to sustain the position of the motorcycle, so the pitch angle, and the second part, which is used to either pitch it up or pitch it down. And if you look at this expression more closely, you can see that this expression is exactly, this is the force, this is exactly the force that is needed to keep this motorcycle upright. So you might want to check this at home with your knowledge from of mechanics. So there's one force here, there's another force here acting on the system, and if you apply the momentum balance, you will see, or you will come up with a result that the force that is needed to keep the motorcycle upright in a static fashion is exactly this one. So I really recommend that you try this at home with your knowledge of mechanics, mechanical engineering, to prove that this is exactly the force. You can see, I just give you a clue, that U times L0 times the sine of phi should be M times G times L0 times the cosine of phi. This is the balance, if you want. So as you can see, you will be able to see this very obviously from this mass balance, if you want to. Okay. So this is the transformation law. Let me just be very quick right now. You can see it's a system of order 2. So again, we have a chain of 2 integrators. So it's always the same story. We assign 2 poles right here. So we have an omega n of pi, a damping factor of 0.7. So we get control feedback. It's always the same fashion how we do it. And we get a nonlinear control law. So it's all, so we, first of all, we get a linear control law in the linearized world. So it depends on C. And then of course we have to add it into our nonlinear transformation as we always do it. So I spared this out for the moment. And let me just show you the results. First of all, this is a typical graph. So we had the idea that we pitch up the motorcycle at 1 radian, so which is about 66 degrees from 85. So it took us, as you can see here, roughly a second. okay? And you can see this is the force that has to be applied. I'm showing you this because in about 5 minutes, I'm going to show you a video how this is done in real time. So I have a nice video of some guys and they show you, they explain how it's done in real time, and it's really done exactly in the way as you can see it here. There's one other option, and again, this is with integration of the control error, which is shown here. And again, it's the same way as I just seen it in the previous example. So we have the same system, because we always have a chain of integrators. It's always the same system like here. So we have a number of poles which are given here. So as this is some kind of fun example, I'm not going into all the details. You apply Ackermann's formula, which you already know from the previous lectures, and then you get a control law. And again, if you want to pitch up the motorcycle in this case, it's a little bit different. You can see the pitch angle here is 1/2 of pi, so which means we really pitch up the motorcycle to 90 degrees. And you probably know this from some motorcycle races. When the race is over, the winner normally does this to amuse all the audience. So they really pitch up the motorcycle 90 degrees, and we just checked whether we are able to do this also in our simulation. Obviously it works. So you see it, pitch it up, there's a little overshoot, so it really goes backward a little bit and then stabilizes. And again, this is the force that is needed, and normally you see there's a very strong spike, and then it goes back in order to balance the motorcycle, okay? And this is a MATLAB example, which will also be distributed for you, so you are able to play around by yourself. And right now I'm only going to show you some video result. First of all, this is the result that you would probably get in your MATLAB if you just invoke MATLAB. There's one way where everything is simulated, and you can see if your version of the motorcycle pitch control works. So you can play around, change damping factors, change whatever you want, and check how the motorcycle reacts. And now there's the real world, which I often like to show. So this is some kind of motorcycle guide that I found this on YouTube that explains the audience on how to do this. So just one disclaimer from my side: don't copy it unless you're very experienced. And let me show you how this guy does
Der
it.
Tank ist voll, also lasst uns loslegen. Beim ersten Schritt, das Vorderrad hochzubekommen, gibt es zwei Möglichkeiten. Einerseits, je nach Leistung, kann man einfach am Gas
So you
drehen.
see what he says? He says ripping your throttle up open is one possibility, and this is exactly what our controller does. It rips open the throttle in order to get the motorcycle.
Ein sogenannter Gas-Wheelie.
Up.
Oder, was mir lieber ist, die Kupplung zu benutzen.
This is not what we do. Let's see what it does. You already heard it. So you really need some kind of very, very strong increase in the acceleration force in order to pitch up the motorcycle. So this is exactly what we also get from our nonlinear controller. Of course, this guy is very experienced. I bet he doesn't know how to do nonlinear control, but at least he knows how to apply it. And again, please don't try it yourself. It's just, again, it's a fun example, but it should show you that this nonlinear control also really works in practice. Okay. So I'm essentially done with the lecture today, and let me conclude by just giving you a very brief outlook what we are going to do next week. For this lecture, I've just told in the very beginning that we assume that our relative degree, so this is the order of the derivative where the system input shows up in the derivative of the output. We assume that this is equal to n. This is an assumption that holds for many systems, and you can see the point was, if this assumption holds, then I'm just winding back, then our state transformation can be obtained very easily. Everything is very nice. Our state transformation is uniquely determined. So we have the output, first derivative of the output, second derivative, all the way through the n minus first derivative. This is very nice. However, if this doesn't work, and unfortunately for quite a number of systems in practice, it doesn't work properly, we have to find other ways. So I'm going back to our lecture next week. And obviously there's a number of ways to do it. And next week, I'm going to show you the Burns-Isitori canonical form. So you can already see what we are up to. So there's a certain number of states where we can still apply the rule that we did today. So C1 is equal to Y, C2 is equal to Y dot. So we can only repeat this game up to a certain number of the output, which is theta. And then, as you can see here, we have to be creative and find some new transformation laws, which we have to do in order to complete everything. And then you can see things will get a little bit more complicated. And I'm going to explain this to you next week, just to show you a little preview on the examples. One typical example where this happens is systems with variable mass. So for example, if you wanted to land this, this spaceship on the moon, which has been done successfully 50 years ago, but also whenever a satellite is launched, a rocket is launched, then there's a significant change of mass in the system while it's launched. You know that probably 95% of a rocket is comprised of rocket propellant. So 95% is burned up until it reaches orbit. And then you have to consider the variable mass. And this is a typical example where the feedback linearization doesn't work the way I've shown it today, but it works in a similar fashion. And this is what I'm going to show you next week. So I think we are quite on time. It's 1:40 p.m. Thank you for your attention, and I'm going to see you back next week. So I'm still open to some questions. If there are some questions from your side, you just feel free to unmute your mic and ask me. So I'm also now looking at my chat window, so if you want to just ask in written form, also feel free to do that.
Question about the exam. How is the form of the exam? Will it be a multiple choice or?
The exam itself, first of all, we still don't know whether we are allowed to let you into the lecture halls. So by now it's not decided, but we will let you know as soon as possible. The exam is normally a mixture of exercise problems and theory questions. So it's not multiple choice.
Okay, thanks.
Yeah. Mm-hmm. Any other questions from your side? There was one, okay. So there was a question, when are the previous lectures and exercises going to be on YouTube? So Alexis, are you still with us?
Yeah. Basically, to answer this question, we did not record the exercises lecture, the exercises session. And for the previous lectures, unfortunately, the last one, the recording just failed. I mean, the audio failed. So this one will be on YouTube, and the next one will be, but for the previous one, cannot. We don't have them. I mean, we did not record them properly.
So Alexis, unfortunately, I couldn't hear you. So when are you going to upload them?
I mean, I will upload this new one, the one we did today, and the one you will carry on. But for the previous lectures, we had some recording problems, so we only uploaded one of them.
Okay.
The other one will not be available yet.
So you had some troubles with recording, but this one will obviously is going to work. So because we tested it, and then you're going to upload it and send the links to the students, so to say, huh?
Yeah, exactly.
Okay, good. Huh? Any other questions from your side? Also, of course, if there are any other questions from it, because we are actually a small group, okay? So if there are any questions from your side, or if you like collaborating in some way and you want to have something clarified, I'm also open to have some kind of, if you want, so private Zoom session where I could explain things. So you all have my email address. So you could feel free to email me if there are some particular questions that show up, or if there are things that are unclear. I'm happy to have some, I would say, separate session where it could be explained. So this is not a problem. Okay. So if there are no further questions at this time, I would say that we are closing this lecture. So thank you for attending and paying attention. And I'm going to see you back next Thursday at 12 p.m. So thank you and have a nice afternoon.